In this video, we're going to take another look at the mod operator. In particular, we're going to look at its relationship with congruence that we did on the last video. So I'm just going to review the connection between the mod operator and quotient remainder theorem, and then also review the connection between the quotient remainder theorem and congruence, and then we're going to put those together and describe what the connection is between the congruence and the mod operator, and that's actually going to help us do some nice computations using the mod operator for really big numbers. Alright, so just as a review, if a and n are integers, I'm using n this time instead of b because that's going to be nice when we start talking about congruence. N is greater than 0, then we say a mod n is the remainder you get when you divide n into a. In other words, when you do the division a divided by n. And so remember, what that means is we have a equals nq plus r, and that tells us then that a mod n is equal to r. R is the remainder. But if you remember that nq plus a equals nq plus r sort of came up when we were talking about congruence. So if you have a and b and n integers, we say that a is congruent to b mod n if a is equal to nq plus b for some integer q, right? So we were thinking of n as the number of days in a week, and so a and b represent the same day of the week if they're basically the same except they're off by a certain number of weeks. nq would be q weeks. So what that means is if you look at that equation, that nq plus b, it looks a lot like nq plus r. So what that tells us is that if x is equal to a mod n, then x is actually congruent to a mod n. So that's going to make a lot easier when we start doing some mod computations. So let's do a puzzle first before we go into those general principles. So let's say I tell you that you have some numbers x and y. I'm not going to tell you what those numbers are, but I am going to tell you that x is congruent to 9 mod 12. I'm also going to tell you that y is congruent to 4 mod 12. And then what I want to do is figure out what is x plus y mod 12. Now this may seem like a really unfair problem because I didn't tell you what x and y are, but turns out I did give you enough information to actually figure out what x plus y mod 12 is. Let's give it a go. So here's what we know. We know that x is congruent to 9 mod 12. Well, what does that mean? Well, the definition of congruence says that it's equal to x is equal to 9 plus 12q, where q is some whole number, some integer, right? X and 9 are either the same number or they may be off by a certain number of weeks. In this case, a week means 12 days. For y congruent to 4 mod 12, it's going to be exactly the same. Y is equal to 4 plus 12. Well, we can't say plus 12q because y and 4 may not be off by the same number of weeks that x and 9 are, but it's going to be 12 times some integer. I'm going to call it p. So y is equal to 4 plus 12 times p. All right. So now let's see what happens when we try to add x plus y. See what we can find out. Well, we just plug in 9 plus 12q for x and 4 plus 12p for y. Well, we can kind of rearrange them, right? We can take the 9 and 4 and add those together. And then we can take the 12q and the 12p and add those together. Now 9 plus 4, that's just going to give us 13, right? And the 12q plus 12p, if we factor out a 12 from that, we get 12 times the quantity q plus p. Now, again, if you look very carefully, this is exactly the quotient remainder form of congruence mod 12. And that tells us that x plus y, we don't know what x plus y are, but it turns out that when you add them together, they're congruent to 13 mod 12. And again, that 13 just came from the 9 plus 4. So in some sense, all we had to do was take the 9 and the 4, add them together, x plus y is equal to 13 mod 12. Now, of course, we want x plus y mod 12, which means we want it to be a remainder. 13 is too big for a remainder. Fortunately, though, 13 mod 12 is 1, and so that tells us that x plus y mod 12 is going to be equal to 1. Pretty nice, especially since we didn't know what x plus y are. All right, let's do another puzzle. So again, we have some numbers x and y. Here's what we know. X is congruent to 5 mod 8. We're doing mod 8 this time. Y is congruent to 2 mod 8. And I want to know, what is x times y mod 8? And what we're hoping is for something similar to what we had when we did addition. And it turns out we do, but we're going to have to work a little harder for it. All right, so here's what we know. X is congruent to 5 mod 8. That means that x is equal to 5 plus, now let's see, so we have 8 days in a week, so q weeks is going to be 8 times q, right? So x is going to be 5 plus 8q. Now, y is congruent to 2 mod 8, and then again here we have y is equal to 2 plus 8p. Again, we use p instead of q because we don't know how many weeks there are between y and 2. All right, so if we multiply x times y, yeah, that's going to be a little bit unpleasant. We get 5 plus 8q times 2 plus 8p. We're going to have to do some foiling. So, okay, so first of all, let's multiply the 5 times 2. That gives us 10. If we do then, the outer one is going to be 5 times 8p. That's going to give us 40p. We do the inner one, that's 8q times 2. That gives us 16q. And then finally, the last one is going to be 8q times 8p. That gives us 64 times pq. Now, that looks a little bit messier than the addition, but it turns out it's not so bad. I mean, everything there except for the 10 is, we can factor out an 8. We can factor out an 8 from 40, from 16, from 64. So let's go ahead and do that, and we get 10 plus 8 times the quantity. Well, it's a big quantity that's a big mess, but the most important thing is it's an integer, which means that x times y is actually congruent to 10 mod 8. And again, that 10 just came from multiplying 5 times 2. And so then if we want to find x times y mod 8, well, 10 is congruent to 2 mod 8, which means that x times y mod 8 is equal to 2. So if we can summarize what we did with all that work there, if you want to find x plus y mod n, for instance, well, first find x mod n and y mod n, then add them together, right, to get some number. I'll just call it r, and then just find r mod n, right? And multiplication is the same way. If we do x times y mod n, find x mod n and y mod n, multiply them together to get some number r, and then find r mod n. And the nice thing is the r in both the x plus y case and the x times y case is a lot smaller than the numbers that you started with, so presumably it's going to be an easier computation. And let's see how we can use these conclusions on a mod operator that before this would be really, really hard, okay? We're going to compute 7 to the 10 mod 5. Now, 7 to the 10 is a really big number. In fact, I bet if you try to put it in your calculator, 7 to the 10 would break, well, it wouldn't break your calculator, but your calculator would not be able to easily handle it. But it turns out without using a calculator, we're going to handle it just fine. All right, so the nice thing about 7 to the 10 is it's just a lot of multiplication, right? You get 7 times 7 times 7, 10 times, okay? Now, if you think back to what we did for multiplication, 7, since we're multiplying it, we can replace each of those 7s with 7 mod 5. 7 mod 5 is just equal to 2, so we can replace each of those 7s with a 2 to get 2 to the 10. And then all we have to do to find 7 to the 10 mod 5 is find 2 to the 10 mod 5. And they're equal. So, and notice that 2 to the 10 is a lot smaller than 7 to the 10. So already we've made some progress. Now, 2 to the 10 is still a really big number. So we're going to try to play the same game with 2 to the 10 as we played with 7 to the 10, except it's going to be a little bit harder because if we try to replace each of those 2's with 2 mod 5, 2 mod 5 is just 2. Which doesn't do us any good at all. But if we're a little bit clever and pair the 2's together, right? We have 10 2's. That gives us 5 pairs of 2. Each of those pairs of 2, 2 times 2 is equal to 4, and that gives us 4 to the 5th. So that makes the exponentiation a little bit smaller. The problem is we still have the same issue as we had before. We can't replace 4 with 4 mod 5 because 4 mod 5 is just 4. However, if we play the pairing game again, we get a pair of 4's, another pair of 4's, and then a singleton 4 left over, and then we end up with 16 times 4, which hopefully is going to be a little bit more manageable. All right, so I'm at a slide. I got to sort of go to the next slide. So remember what we have is 7 to the 10 mod 5 is the same as 2 to the 10 mod 5. And 2 to the 10 is equal to 16 times 16 times 4. And the nice thing about those 16s is we can replace them with 16 mod 5, which equals 1. That's actually nice. So right, because 5 goes into 16 3 times to give us 15 with a remainder of 1. And that means we can replace each of those 16s with a 1 to get 1 times 4, which just equals 4. And then that gives us 7 to the 10 mod 5 is equal to 4. So with some pretty simple computations, we can do what seemed impossible at the beginning. All right, so now I think you're ready to work on the activities for the mod operator and congruence of integers, and that's on the PDF file included with this video.